Cool. So we have I think this is the name. It's a tutor institution. And they have a list of problems. And if you solve any one of them, you get $1 million prize. And so they call the $1 million problems or the Millennium Prize problems. And out of all the problems, only one of them has been solved, which is the
Pointed conjecture.
yes. So this is the only one that has been solved. Although there are a few people who believe that the proof has not yet been verified well, and it may still not be solved. But let's just be optimistic and say it's solved. And that there are other such problems. Can someone name some other problems?
Yeah, the one is Riemann hypothesis.
Yes. So I think this is one of the most
Yeah,
famous
famous.
Millennium Prize problems.
Hodge conjecture.
I'm sorry, what?
Hodge conjecture.
Yes. Okay. What else?
Navier-Stokes.
Yes. So you have the Navier-Stokes equation. Existence and smoothness. So these all sound really fancy, and they're hard to even talk about, like even to describe what the problem itself is, especially for these two, even the Riemann hypothesis, because it I mean, okay, I mean, I guess someone could state it for you, but you need to know some complex analysis to understand what's going on. And then there are a few other Millennium Prize problems, such as Yang-Mills existence, and yeah, so there's also Swinnerton
But
conjecture, and yes, Burton-Swinnerton yeah, and yeah, but what we'll be talking about is what's the P versus NP problem. The goal of this talk is to introduce you to what complexity theory is, and in particular, introduce you to it through this problem of P versus NP. Okay, so yeah, so it's commonly believed that talking about the easiest problem to describe to someone who's not in the field of mathematics or computer science is this problem of P versus NP. So this is in some sense the easiest to describe, but I said second easiest because there's one problem that has been solved. So it's only fair to call that the easiest, even though the proof is nothing close to being easy. Okay, so yeah. So as the description of the talk said, let's talk about Sudoku. And let's just not talk about a 9x9 Sudoku. Let's talk about generalized Sudoku. So what does generalized Sudoku mean? It just means that instead of a 9x9 grid, you have an n square cross n square grid. Right? So for any natural number n, and your entries. So does everyone know how to play Sudoku? If you don't, I can describe it.
Yeah, like probably.
Okay, so for the sake of brevity, let me just describe it anyway. So you have an n square cross n square grid divided into n square blocks of n cross n squares. For example, this would be the grid for n equal to 4, where each of these unit blocks are 4 cross 4. So this is in entirety a 16 cross 16 board. And we put numbers from 1 to 16 in each cell such that each row has numbers, all numbers from 1 to n square occurring in them, which also means that there can be no repetitions, because if you repeat, then there will be some number that will be missing from that row. And then the same thing holds for each column. And it also holds for each block of n cross n square. So this is a block. So this holds for this. And yeah, so this is, yeah, so the goal, so the input is usually a partially solved sudoku, and the goal is to completely solve it, right? So, okay. So we've described the problem statement. And the thing is that, okay, so what are your thoughts on how you would go about solving it? So, okay, let's just talk about the regular 9 cross 9 sudoku. How do you usually solve these sudokus? So
Like
when
we
you
write what the possible hints are and then fill in.
could you be more precise? Exactly what do you do?
Like if a row
Your
has,
thought process.
so if we consider all the rows one by one, and suppose we consider row one, the numbers there are 1, 3, 5, and we are analyzing a particular cell. So we write the remaining numbers in that cell, like, and then we analyze the column associated with that cell and the block. And if we are left with one number, we fill in that number.
Yes, so that is one possible strategy. So you look at a cell and you look at the block. So look at the column, look at the row, and look at the block it's inside. So we know that this cell cannot have a number which is equal to any of these numbers, right? So if we are lucky, so if there is only one possibility, then that's great, because then we can just fill it in, right? So this is a good case, because there's just one possibility, you fill that number. There are other strategies. So for example, suppose you have so look at the first 3 rows. It looks like this. And suppose you have a 1 here, a 1 here, and then you have a 2 and a 8 here, right? So then you know that there must be a 1 here. Why? Because note that this cannot have a 1 anywhere, and then this cannot have a 1 anywhere, but then we need a 1 in this row. But we already said that there cannot be a 1 in any of the first 6 cells, and the last 2 cells are already filled. So then this must be a 1. So this is also a good case for us. But now the problem is that these cases may or may not occur anywhere, right? So nowhere does this strategy of ours guarantee that this happens, right? So what do we do once we get stuck? For example, so for example, we have a list of different things that we can do, and in any of them, if there's a single possibility for a cell, then that's great, because we can proceed. But what happens if we're not able to proceed? So what do we do? If our heuristics don't work, because none of these things that we talked about are actual foolproof strategies, right? So because they may or may not occur in the grid that we're solving. So can we do better? Is there a proper algorithm? So think of like the stupidest algorithm. Like, how do you solve a Sudoku?
Fill in like every possibility, check every possibility.
Yes, you can do that, right? So suppose you have m missing cells. So m, uh, sorry. Suppose we have m missing cells. Then for each of these cells, we have 9 different possibilities, right? In general, n square different possibilities. So then we have in all n square raised to m different ways of filling them, right? Not all of them will be valid, of course. N square different ways of filling them. And then we can test out each of these possibilities and see if any of them works, right? Check each. So now what is the problem with this? It is a correct algorithm, so it is correct. But what's not good about it?
If n is very large, it's like manually impossible to check.
Exactly. So it's in some sense infeasible, right? Even though we have a solution, it's in no way a solution that would ever be used anywhere, right? Because even just consider your regular 9x9 Sudoku. In general, in a newspaper puzzle, it's usually half of the cells are missing. Maybe let's say about half the cells are missing. So let's say about 40 cells are missing. Let's even say that only 20 cells are missing. Then we check for 9 raised to 20 possibilities. That's huge. Possibilities. Too much. It's too much even for a computer. So usually the standard is that a computer can do something like, let's just say 10 to the 9 instructions every second per second. A regular computer, so our regular computer can do this. So even for a regular computer, it means that it would need 9 raised to 20 over 10 raised to 9 seconds to do it. It will actually be much more. There will be some big constant here because an instruction is a very small thing. It's like changing a bit or something, while these are manipulating numbers. So it's it. So, but let's even forget C for now. So how much is this? Can someone input this on the calculator and tell me? Actually, let me do it as well. So it is more than 10 to the 10 seconds. Oh, sorry. It's more than 10 to the 10 seconds. And just to tell you what this scale is, 1 year consists of about 3.16 or something into 10 to the 7 seconds. So then this would correspond to about more than 300 years to solving a single Sudoku by a computer, right? And remember that I only took 20 here. Usually the number of missing cells are much, much more than 20. So even if it's 40, this sort of multiplies this by 9 to the 20. So then this gets multiplied by 9 to the 20, which is more than the age of the universe. So yeah, so obviously there's a problem here. The problem is that these algorithms are not feasible. Oops, sorry. Okay. So we talked about one problem, and oh, by the way, for an n cross, so you must be wondering if there is some way of solving n cross n Sudoku. It turns out that despite Sudoku, Sudoku has been around for a long time, and I mean humans, so we do not know a good way of solving a general n cross n Sudoku, n square cross n square Sudoku. That is, any algorithm for Sudoku still takes a long time. So by long, I mean it's usually exponential in n. So even if it's something like, so I know that the most naive method that I told you took n raised to 2m time, which is at most n to the 2n square. But there are algorithms that can do much better than this. Even then, the best algorithms known cannot do it in, say, polynomial number of steps. So the best algorithms known take exponential number of steps. And we don't even know how to prove that this is the best. So we have not proved that there is no polynomial time algorithm for there's no fast way of solving an n square cross n square Sudoku. But this is the best we know so far.
Is there any particular strategy?
Usually the ways to solve these are by these heuristics, but you can complicate the heuristics more, and you can prove that if you keep applying these heuristics, then there are many different sorts of heuristics to solve these, and there is no particular method that does it better than anything else. Basically you try to enlist like 10 or 20 different such heuristics and try to keep applying these heuristics each step, and then try to prove that under those heuristics you can do something like, say, n to the 2n, for example, instead of n to the 2n square. Even then this is like exponential, right? Because n to the n is like an exponential function. There's no good general way of solving Sudoku fast. As n grows, eventually this will be something which is infeasible for the computer for relatively small n. So maybe even like a 50 square cross 50 square Sudoku is too hard for a computer to do, for a computer in the current world to do. Okay. So we talked about one problem which we think is difficult. Let's talk about a problem which we think is easy, which we know is easy. It's the sorting problem. Sorting. Okay, so we're given a list of numbers a1, a2, up to an. And we want to sort them in ascending order. So want to sort in ascending order. How do we do this? What's the most natural thing that you can think of? So if you're given a bunch of numbers, then what is it that you try to do to sort it? So you're given a bunch of scattered numbers everywhere.
We pick the smallest and put it at the start, and then pick the second smallest and so on.
Exactly. So out of these numbers scattered everywhere, you find the smallest number and then you put it in the first place, and then you find the second smallest number, and then the next smallest, and then the next, and the next, and the next, right? So that's what we do here. So we go from left to right and remember the smallest number we have seen so far. And once we've gone from left to right, we come back to the smallest number we saw, and then we put it on the first position. Right? So let's take an explicit example. Let's say we have 1, 5, 2, 3, 4, or actually, let's do 5, 1, 2, 6, 4, 3. It doesn't matter. The numbers don't have to be from 1 to n, but it's just for the example. Okay, so I maintain something called, so I maintain the smallest number I've seen so far. So when I'm here, the smallest number that I've seen is 5. And the index where I saw it is the first position. So it's the first position. And the smallest number is 5. Then I move to the right. And then I notice that now this number is smaller than what I saw before. So I update this. So now the smallest number I've seen is 1, and it's at the second position. And then I move to the right. And this is a 2. It's not smaller than what I saw. So I keep moving to the right. Then move to the right and see 6, 4, and then finally I get to the end. And this is also not the smallest. So then since I've come to the end, this means that the smallest number is on the second position. It's a 1. Right? So since I know the position number, I can simply exchange whatever is in the first position with this. Right? And then so after exchanging the numbers, I have 1, 5, 2, 6, 4, 3. And then I repeat the procedure on this. Right? So it's sort of iterative or recursive in some sense. Right? So to sort n numbers, I go from left to right and then find where the smallest number is, and then put the smallest number at the beginning and the first number where the smallest number was, and then sort the other n minus 1 numbers. So how many steps does this take? Like, think about checking each number as one step. So
n factorial steps?
no, we actually do much better than n factorial.
N square.
Why is it n square?
Because we pick the smallest and we have to bring it to the start.
Yes. So how much time does that take?
To bring it to the start, we could keep exchanging. So it will take n steps to bring it to the
Yes.
start.
Yes. So finding the smallest number and bringing it to the beginning took n steps, right? So we checked all n different numbers, and then we brought this to the beginning using one more step. So the number of steps taken to go from this configuration to this configuration, that is, in general, if I have any list of n numbers. So if it is confusing as to what our model is, think about these as cards. Think about them as cards. You have n cards from like kept in a row, and they're all face down. So think about face down cards. And your goal is to eventually sort the cards from left to right in ascending order of whatever is written on them. So, but the problem is that they're face down. So at each step, you'll have to turn a card and look at the number which is there, right? So So think about the fact that every time you turn a card, that counts as one step, right? And then when you turn the card back, you forget. So you kind of so the idea is that to find the smallest number, you'll have to turn all of the n cards and then bring the first card at the beginning and then sort the remaining n minus 1 cards. Right? So basically finding the smallest number and bringing it all the way to the first position takes some linear number of steps, say n step. Maybe it takes like 3n steps or something. It doesn't matter. I'll just write it as n. The constants don't matter to me so much. It'll be some c times n plus d. It doesn't matter what the c and d is. It's fine. It is upper bounded by this, right? And then once I have this, I have the smallest number here, which I will never move. Let's call the smallest number b1. And then I have the remaining numbers here. Let's call them b2, b3 up to bn. And this sequence is really a permutation of the beginning. I'm just renaming them because the numbers themselves might have changed. And now I sort on this remaining n minus 1 numbers, right? So doing this again takes some, so finding the smallest number in this list takes some c times n minus 1 plus d steps, so on all the way to some c times 1 plus d. Right? So the total number of steps taken by my algorithm, number of steps, is no more than c n plus 1 over 2 plus dn, right? Which is less than equal to some an square plus bn plus k for some appropriate a and b and k. And so what this means is that there is a
Where does that K come from?
I mean, k can be 0, it's fine. There's just some reals a, b, k. So the point is that this means that there is a quadratic time algorithm to sort a list of n numbers n elements, or let's say numbers. And this is really good. Quadratic is good because remember before, even on n equal to 3, the stupid algorithm that we have went up beyond the age of the universe. But here, even if n is as large as 1,000 or even 10,000, this means that we have an algorithm which takes like 10 to the 8th steps or something. Maybe some constant times 10 to the 8th steps. For this C is different from this C. This and this are different. But so then a computer that takes 10 to the 8 and 10 to the 9 instructions would solve it in C by 10 seconds. That's really good, actually. So even if the input size is this huge, we are able to sort the number. In fact, even though I told you that for n numbers, it takes something like an square plus smaller terms. So note that here an square is like the largest term eventually, right? Maybe for some small n, b times n may be larger than an square. The point is that eventually an square is the term that will matter, because as n grows, an square will be much more than bn or k. So it actually turns out it's a fun exercise. So that we can improve this to a times n log n plus smaller terms. Although it's not relevant here. This is just a fun fact. Okay. But, okay, so let's sort of just summarize what we saw in the two problems so far. On one hand, we have sudoku, and on the other hand, we have sorting. So we saw that here we do not know a method to solve it in polynomial number of steps. On the other hand, for sorting, we just saw a polynomial time algorithm. Quadratic is polynomial, right? So we have a quadratic time algorithm, and in particular a polynomial time algorithm, which is why this n log n didn't matter to me. I don't really care as long as I have something which is at most a polynomial. Right. So it seems as if these are like two different problems, and Sudoku is probably like much harder than sorting. However, there is one thing which is common to both of these. Suppose I tell you, okay, so suppose I give you a solution to a Sudoku. So for example, I have some Sudoku that I want to solve. It's like partially solved with some numbers here and there, whatever. But now suppose some friend of yours comes and tells you, hey, look, I found a solution to the Sudoku. Everything is filled, whatever. Everything is filled. Of course, your friend may not be perfect. Maybe there's a mistake in the solution. But given that your friend has told you this solution to this problem, can you check whether this is a valid solution? Can you tell me a method to simply check if the solution is correct?
We check every cell.
Okay, and what do you check about each cell?
Like in that row, that element occurs again or not, in the column, in the block.
Yes, so obviously you'll check if each element, so each number in 1 to n square should occur in each row, column, and block, right? But there's also something else that you need to check. What is it? You need to check if it's a solution to this problem. This can't be just a general solved Sudoku, right? So that means that for each filled entry in the problem, so let me call this the problem. Sorry. Let me call this P. Let me call this S. So each filled entry in P, the same entry should come in S, right? Otherwise, I'll just give you a solution to a random other Sudoku, and it doesn't solve this Sudoku. Right? The same entry occurs in S. And how much time does this take? Do you see that this is polynomial? Like, it shouldn't be too hard to check, right? So you just have to go through each of the cells, and for each of the numbers, you have to check whether that number occurs in that row or not. So to check if one occurs in a row, you just go through each of the, so say if you want to check if one occurs in the first row or not, what do? You simply check if this one is one of the numbers here, right? So you go through each of the n square cells. So to check if one occurs in the first row, it takes n square time. To check if one occurs in any of the rows or any of the columns or any of the blocks, it will take n square times number of rows plus number of columns plus number of blocks time. And how there are n square rows, n square columns, and n square blocks. This is just to check if the number 1 appears everywhere, and then you have to check for each of the numbers. So then you'll also multiply this by n square for each number, right? So then this is something like 3n to the 6. This is polynomial. Great. And obviously, checking if an array is sorted is easy. If you can actually sort it, then checking if it is sorted cannot be harder than actually sorting it, right? So checking a solution, so that is, if I'm given an array A and your friend comes and tells you an array A prime, and this friend of yours tells you that this A prime is sorted, you need to check if that is true. You can simply sort A on your own and then check element-wise whether your sorted array and the array that your friend sent you or told you is sorted matches or not, right? A prime is A, which is sorted, right? So yeah, so if you can solve a problem fast, then you can also check it. But notice that for Sudoku, we don't know how to solve it fast, but we know how to check it fast. Right? So there is something which is the same between them, and there is something which is not the same between them, or we believe is not the same between them. Well, not everyone believes it. We'll talk about it. Okay. This brings me to defining P and NP. So let's start by defining P. So the P, which is also called polynomial time, the shorthand for polynomial time, it's the class of all problems, those problems that can be solved using polynomially many steps. Using polynomial number of steps. So sorting, for example. So sorting is an element of P. Know that P is a class of problems. So any problem that can be solved in polynomial time would be an element of this class. Can you tell me some other problems that you think can be that can be solved in polynomial time?
Checking a Sudoku, as you told.
Yes, sure. Yeah. Check Sudoku. Something else? There are so many mathematics problems. Just think of any one and let's just so maybe even if you're not sure if we can do it in polynomial time, think about any such problem.
I'm not sure about this, but how about checking if a graph is a tree? Is that
Yes,
polynomial?
good. Yeah, it is polynomial. Checking if a graph is a tree. Turns out that we can check fast if a graph is a tree or not. Well,
This problem is polynomial in what? In the number of
polynomial is the
nodes?
size of the input. Yes, so number of nodes and edges. Yeah, number of nodes. So there is some polynomial f such that for any graph G on n vertices, checking if G is a tree takes at most f of n steps. For example, for sorting, we saw such an f, which is of the form an squared plus bn plus c. We said k, but okay. Good point. I will include this in the notes how to solve this in P if it's not clear why it is in P. But can you think of some other problems? How about this? I have a list of n numbers and I have a target sum t. I want to know if there exist two distinct indices whose sum is equal to this target. This is polynomial time, right? This is again a quadratic time algorithm.
Yeah, you can just check all pairs.
Yeah, I can just check all pairs. Right? So this is what is called the two-sum problem. Of course, even three-sum is in P. I know I'm mentioning three-sum differently, but three-sum is a very important problem. Not for this talk, maybe for some other talk, we could talk about three-sum. Okay. Let's go for one or two more examples.
Checking if a number is prime.
Okay, good. How do you know it's in P?
We can do it in square root n.
Okay. So here is the problem with that, right? So it is actually true that checking if a prime, if a number is a prime is in P, but not for the reason that you thought. So what is the input to a number? So usually what you do is that our input is a number n. Oops, sorry. Input is n, and our output should be 1 if n is prime and 0 otherwise. But what is the size of the input really? Is the size of the input n, or is it the number of bits needed to represent n? So if, for example, say if n is 1024, then you only need 11 bits to write it, right? You write this n like this in base 2, or let's just stick to base 10. So let's say if n is, say, this large, then you only need 6 bits to write it, right? So your input really has size 6. Your input size is 6 and not 10 to the 5. So your algorithm should actually be polynomial in the size of the input. This is our input really, right? So this is crucial. This actually talking about primes is a good point. So we need our algorithm to be algorithm should be polynomial in the input length. Yes. So for the primes problem, that is, if you input a number and it should output whether it's a prime or not, the input is actually log of n bits and not n bits. So yeah, you're right in the sense that you're right that there is an algorithm for primes which goes like this. You check for each number from 1 to root n, from 2 to root n. You check if I divides n or not. And if any of those I divides n, then n is not prime, right? Because then you found a non-trivial factor. But the problem is that even though this takes root n steps, it's actually root of 2 raised to the size of the input, which is like 1.414 raised to the input size, which is an exponential time algorithm and not a polynomial time algorithm. Even so, this is still true. So there is an algorithm for primes that actually takes time, which is only polynomial in the log of n. And it was a great result proven by Indian theoretical computer scientists, Agarwal, Kayal, Saxena, 2002 or 3, I can't remember. And yeah, this is a great result. In fact, 2 of them, Saxena and Agarwal, are professors at IIT Kanpur. Kayal works in Microsoft Research. It's really cool. Yeah. So this, prime is in P. So you were correct, but the algorithm itself is not exactly correct. Yeah, the algorithm is much more involved and it uses a lot of algebra and binomial theorem and Fermat's little theorem and the idea of generators. It's really cool. Okay. So I think this is enough number of problems that are in P. I will not put an algorithm for this. I will put an algorithm for the check tree problem. In fact, I'll put it as an assignment and then I'll also post a solution. Okay, cool. So we now know what the class P is. Let's talk about what the class NP is. NP is the class of problems. So whoa. Okay, I'm just lazy. Okay, so this is NP, and this is no longer called polynomial time. It's called, so a lot of people think it's called non-polynomial time, but that's not the name. It's not called non-polynomial time. It's called non-deterministic polynomial time. I will not get into why it's called non-deterministic. That's it. The name, why the name is non-deterministic polynomial time is a little more involved, but the definition is not very complicated. So instead of solved, so class of those problems whose solution can be checked using polynomials number of steps is an NP. That is, you don't need to solve the problem itself, but suppose someone gives you a solution to the problem, all you need to do is to verify whether the solution is correct or not. So let's go back to the Sudoku example. We didn't really solve Sudoku on its own, but given that someone told you a solution to the Sudoku, we were able to verify whether the solution is correct or not using polynomial number of steps. So yeah, so NP is a class of problems whose solution can be checked using polynomially many steps. So again, so we already put Sudoku here. In fact, we also put sorting here. Because if someone gives you a solution to the problem, you can solve sorting on your own and then compare it term by term to the solution that was given to you. What else? So essentially that would mean that everything here is there, right? What this means is that we already know that P is a subset of NP. Because if you know how to solve something fast, so why is this true? So let me write it explicitly. Suppose we know, okay, suppose we know how to solve something fast, solve a problem, let's say, let me not confuse it with the P. Let me call the problem B, fast. Then we can also check if the solution provided to it is, we can also check fast how to solve the problem, right? Because what we can do is to check if a solution is a solution to B, we can solve B on our own and get some S prime. And then we can check if S is equal to S prime. This assumes that there's a unique solution. We assume that there is a unique solution. But yeah, assuming that there is a unique solution, all you need to check is whether S and S prime are equal or not, right? Does this make sense? So this is a whole, so yeah, so this would imply that P is a subset of NP, right? And the question, yes.
Quick question. What if the problem that is, in P does not have a unique solution? But P should still be a subset of NP, right? So how will that work?
Yes. So, okay, that's a good question. So, so let me formulate it in this way. Usually, so okay, so there is a technical reason to that. So for this talk, since it's for everyone, I did want to get into the technical reasons, but let me just mention it in words that usually when we talk about problems in P and NP, we're talking about problems whose answers are yes or no. So instead of actually talking about whether there is a solution to a sudoku, we usually give a sudoku as an instance and ask whether there is a solution to it or not. We don't care about whether so we don't care about finding a solution. We only care about whether there exists a solution or not. So then that is always unique, right? There's either a yes or a no.
Yeah.
Does that make sense? Okay. Yeah. But for this talk, I didn't want to complicate things. Yeah.
Got
So yeah. Okay. Cool. So okay. So we define NP and we define P here, and all that the Millennium Prize problem is asking is P equal to NP? Should have used bold font for this. Okay. So what are your thoughts on it? Do you think it is equal, or do you think it should be harder, that these problems that we don't know how to solve but can only be checked, it's just unusual that things that you can only check are correct can also be solved easily? So any thoughts? Okay, so there's one person who thinks that they're not equal to each other. Okay. There's one person who thinks it is. Okay, good. Any other thoughts? Okay, so yeah, so since this problem is new to you, a lot of you don't even know which direction to think about, whether it's yes or no. So I will tell you that statistically, more people think that think that P is not equal to NP. And then the second most popular vote is that P is equal to NP. And there's also a third vote. What does that mean? So what do you think this third vote is?
P can be equal to NP.
I mean, that's not a vote. That's not fair. Of course, that's always true. What do you mean by can be equal?
And like maybe after so many years.
Well, no. So the P
does it-
versus NP problem does not depend on whether your computer is strong enough or not. The P versus NP problem is really asking if there are polynomial time algorithms to this, like a theoretically polynomial time. So even though your computer may be able to eventually do exponential time algorithms, even if that's not true, but just for the sake of argument, even if it could do that, that would still not prove P equal to NP. P equal to NP is really asking if you can solve things in polynomial time which are in NP.
Yeah, so is the
Yeah.
third possibility that it cannot be checked. Even if it is true, it cannot be checked. And even if it
Yes.
is not
So,
true, it cannot be checked. So
P versus NP is. So again, I won't get into what this means, but independent of ZFC. So yeah, so this is something I won't get into. So this means something and relates to incompleteness, and something relates to incompleteness. I think one of the maths channels on YouTube talks about this. I think the title of the talk is of the video is like maths has a major flaw or something. Maths has a major flaw. I will encourage you to watch the video. I see. So the channel name, according to one of you, is... Oh, isn't it? Isn't this the spelling? I'm not sure. Let me check.
What is ZFC? Can you replay it? Can you repeat?
So I didn't define what ZFC is. I didn't want to get into it, but ZFC is like the axioms of set theory that we use. So it's called Zermelo-Fraenkel set of axioms. Let me put a link to this video. It's a 30-minute video. You can watch it in your... I'll just put it in the chat on Discord later. Okay, but this thing itself is like a very, very interesting thing. And there's a lot of mathematicians, logicians, and even theoretical CS people who work on this. Okay. Okay, great. So I have 30 minutes remaining. I won't take all 30 minutes, but I'll spend the next 15 to 20 minutes talking about how we can even approach this problem, because these are like classes of problems, right? It's so generic and so general. Like, it's a class of problems. How do you even try to prove that two classes of problems are equal? Like, do you prove it for every problem that okay, for each problem in NP, it is in P, and so P equal to NP? Of course, that's infeasible because these are infinite sets, actually. An interesting question would be to ask what the cardinality of the sets is. So, but okay, let's not get into that. You can actually figure that out if you have some idea about, my view on P versus NP. My view is that P is not equal to NP. especially because I come from a complexity theory background, and in complexity theory, everyone believes. Oh, oops, I turned on the captions by mistake. In complexity theory, almost everyone believes that P and NP are not equal. So, yeah, my belief is that I am here at my current stage in time, but yeah, I mean, I'm only starting my PhD. What do I know? Okay, so great. So the remaining 15-20 minutes, we talk about how to approach it. Such a generic problem. And I want to talk about two particular problems and do like a combinatorial exercise right now. So this would be something which is interesting for you to see. Okay. So so let me describe what both of these problems are. There is a problem called the three color problem. So suppose I have a graph G. Any such simple graph, let's say, undirected for now. Can I use three colors? So, and I have three possible colors. I'll use red, blue, and black. And I want to color each vertex in such a way that no two vertices that have the same color are adjacent to each other. So that is, I'm not allowed to do something like color this red and color this red as well, because they have an edge in common. So then this would violate the rule of the game, right? So it turns out that you can three color this. So in fact, it's not too hard. Let's say this is blue, this is blue, this is blue. And this is a valid three coloring, yes? So basically my input is a graph G and I output yes if I can color it using three colors, and I output no if I cannot do it using three colors. So an instance where I will output no is this. Right? Because all vertices are connected to each other. So by pigeonhole principle, some two vertices will end up with the same color. So this cannot be three color, but this can be. Okay, so I have three color. So is this an NP? Suppose I give you a solution to it, which is a coloring of the graph. Can you check if it is a valid coloring or not?
Yes, we can just pick every edge and confirm.
Exactly, right? So even though coloring using three colors doesn't seem obvious, it is easy to check if it is three colorable, right? If I have a graph and if it's already colored, for each edge I'll just check if the colors on the two endpoints are distinct or not. So checking it is easy. So that would mean that three color is an NP. Great. So this is one problem in NP, and we don't know a polynomial time algorithm to this, unfortunately. So we don't know how to put it in P. Okay. And let's talk about another problem called 3-SAT. I'll tell you why I'm looking into these specific problems. So the 3-SAT problem is described as follows. I have what are called clauses. And each clause contains three variables. Let's say x1, x3, x4. And I OR them. Okay, So let me start with something simple. Let's try to interpret what this means. Yes. So it's important to know what 3-sat is for a reason I'll tell you. So each of these xi is a true or a false. And I want to know whether I can substitute the variables in a way that this expression is true. How do I do that? So what does it mean for this to be? What does this mean? So what does an or mean, right? An or means that you need one of the things to be true, right? So if for example, if I get a 90 on a test, or I get a 95 on a test, or I get 100 on a test, then I'm happy. So I only need one of these to be fulfilled. Or if I say, if I get 100 in science, or I get 100 in maths, or I get 100 in English, I'm happy. So this is an or of the statement. So even if one of them is fulfilled, then the whole expression is fulfilled, right? So think about this as, if I get 100 on a maths test, or so it's a not. So let's say x2 was talking about getting 100 on a maths on a science test. If I do not get 100 on a science test, or if I get 100 on an English test, and I'm happy. So each of these xi's are true or false, depending on whether I actually got 100 in that particular test or not. So then, when is this whole expression true? There are many possibilities, right? So maybe if I get 100 in a maths test, then this whole expression is always true. So let me rewrite this as I get this much. So let's forget the ifs. And I make such a claim. So then I only need to check it, right? So okay, so I have like 8 different possibilities of substituting variables here. Right? And then I have this expression x1 or not x2 or x3, right? And can you tell me the value of this for each of the substitutions? So in which of the cases am I happy, and which of the cases am I not happy? So I'm happy in this case, right? Because if I did not get 100, since x2 is the statement that I get 100 on a science test, and I said that I'm happy if I don't get 100 on a science test. So this is a good case for us, right? These are all good cases for us because I said that if I get 100 on a maths test, then I'm happy. And then this is also good because I said that if I get 100 on an English test, then I'm happy. This is the only case where I'm unhappy because I do not get 100 on a maths test. I get 100 on a science test, and I do not get 100 on an English test. So none of these get fulfilled. So this is the only case where I'm not happy, right? So let me put 1 for happiness and 0 for not being happy. Okay, so let's look at a more complicated example. I can make things a little worse. Yeah, okay, I'll tell you what everything means. Okay, here I have an and of or. So the basic premise is that for each x1, x2, x3, x4, I have a list of values that it can be. For the sake of it, let me enumerate it. It will take a while. Let's just do it for 4 values for now. And then I have this whole expression E. And I can substitute these variables in this expression and check what the value is, right? So let's substitute 0, 0, 0, 0, 0, 0, 0, 0, 0. Yeah. So what happens to the first thing? Note that, so okay, so by the way, the bar on top of the variable means a not. So this x2 hat is the same as, not hat, bar is the same as not x2. Yeah. So if x2 is 0, then not x2 is 1, right? So then if not x2 is 1, then this whole thing is a 1. Yes. Similarly, look at the second bracket. x1 is 0, not x2 is 1, and x4 is 0. So this whole thing is a 1 because it's an OR. So I only need one thing to be satisfied. And again, x1, x3, x4 bars are all 1s because x1, x3, x4 themselves are all 0s. So this is also a 1. And I have an and between all of them. So when I say an and, then I need all of them to be 1s. And indeed, all of them are 1s here. So then this expression of mine becomes 1. Does this make sense?
Why are we not considering that x1 ones and x2 ones?
Oh, this is just this example. This is just this. For this substitution of variables, E is 1. I'm considering everything. I didn't write all of them. Oh, sorry. 1, 1, and then 1, 0, 0, etc. I'll have 16 different possibilities, right? So for each of them, I will write what E is. Yeah. So I will have a list of 1s and 0s here. Yes. So the 3-sat problem asks this. So suppose I have, so 3-sat is this. I have a list of M. So by the way, this is called a clause. So I have a list of M clauses, C1, C2, up to Cm. And each clause looks like the OR of 3 things. It looks something like this. It may also look like not. So you're allowed to have nots on the variables. Or maybe it looks like x1. So maybe C2 is this, C1 is this. Maybe C3 is x2 bar or x5 bar or x3, whatever. Yeah. So I have and then I AND all of them. Right? So then AND. So what this means is that it's like a bunch of ORs and then it ANDs between them. So there are 2 ORs in each of the clauses. Yeah. And it's called 3-sat because each clause has 3 variables. That's why the name is 3-sat. And I want to know whether, so the question is, okay, does there exist an assignment to the variables assignment of ones and zeros, that is, and zeros to the variables. Let's say there are n variables, x1 up to xn, such that this clause, this whole thing, let's call it E, is true. That is, I only want to know if, by true I mean 1 is 1. So in particular, for example, this was satisfiable because I found a substitution of variables for which E is 1. In particular, this. So if any one of the assignments makes the expression 1, then I'm happy. So in particular, for this, the output should be yes. So in general, I want to know whether the output is yes or no.
If all the variables are independent, then it is true, right?
You may have repeated variables here, right? So this variable comes here as well.
I see.
So there are problems. Yeah. So the clauses may share variables. Yes. So yeah, that's the problem. Clauses may share variables. Clauses may share. Otherwise, you're right. If the clauses don't share variables, then for each clause, you can make the first thing true, right? So yeah, but the issue is that clauses share variables. So if you try to make one clause true, maybe if you've made like some 10, 12 clauses true, and you made some substitutions to the variables, then that causes something else to be false. So, and there is no way to do anything about it. So that's a problem. So think about this. This is not a 3-sat instance, but think about this. X1 or x2 and x1 or not x2 and x1 or x2 and it turns out this is never satisfiable. So this is always 0. So then this corresponds to the no instance. How about this? How about if your friend comes and tells you that, look, this assignment works. Can you check if it works efficiently?
Yes.
Yeah, you just plug the variables and check for each clause, and then do a land of them. So it's very easy to check. But again, it's not easy to solve it because the brute force method to solve it would be to test all 2 to the n possibilities. Right? So that's too much. 2 to the n is exponential. So 3-sat is in NP, 3-color is in NP. And the reason why I told you that 3-sat is NP is that the following theorem is true. I will not prove it. I'll just state it and end the lecture. That if 3-sat can be solved in polynomial time, then any problem in NP can be solved in polynomial time. So it's really a crazy theorem, right? Because time. So it's crazy because NP has such a huge class of problems. There are infinitely many problems in NP. The point is that this theorem has managed to show that proving that 3-sat can be solved in polynomial time is equivalent to saying that P is equal to NP. By the way, this is called Cook-Levin theorem. I do not remember when this was proved, but it's such a simple statement. This means I've managed to take out one particular problem. So 3-SAT is one problem, in which sense it's like the hardest problem in NP, right? It's the hardest NP problem. Because if I can solve this hardest problem, that is, if I can solve 3-SAT in polynomial time, then I can solve anything which is in NP in polynomial time. So in some sense, 3-SAT is the hardest possible problem in NP, right? So such problems which are the hardest NP problems, 3-SAT is not the only one. There are other problems that are hardest. For example, remember when we talked about 3-color? So 3-color is also hardest. Also one of the hardest NP problems. And there are many such problems which are hardest. So do you know what a there's a person with a username Hamiltonian path or something. So there is a problem called Hamiltonian path problem. Given a graph G, is there a path that goes through all vertices? Such a path is called a Hamiltonian path, and this is also one of these hardest NP problems. And there are like thousands of these problems. There's a whole book of problems which are these hardest NP problems. The whole book on it. The book just consists of problems. Of course, they prove why. Actually, that I don't think that book itself proves it, but there are proofs as to why these are hardest. And all these hardest NP problems are what are called NP complete problems. That is, NP complete problems are the set of those problems such that if you can solve them in polynomial time, then you can solve anything else in polynomial time. So this is one approach to resolving P versus NP in the side that Pranav suggested, that usually to tackle and prove that P is equal to NP, you try to tackle one of these problems and prove that that can be solved in polynomial time. And the reason why most people don't believe that P is equal to NP is that we have had these list of 1,000 problems for many, many years, yet not a single person has been able to solve any of these problems in such a long time. Right? So usually when something like this, of course, it's more of a human element here that look, humans are not able to solve these problems. Maybe it's not our fault. Maybe these can actually not be solved in polynomial time. But it is intuitive to think about it, right? That there's this huge list of problems that we're not able to solve, then probably it cannot be solved. And the reason why people think P is not equal to NP is that we've had these list of problems, of thousands of problems, for many, many years, for maybe 50, 60, 100 years. I mean, these problems like Hamiltonian path problems have been around for like centuries. Right? So this stuff, but I don't think people before a century have really put thought into how fast we can find a Hamiltonian path. But yeah, but we have these lists of 1,000 problems for a long time. Yet nobody has been able to solve it. So this is in support of P not equal to NP. There is also a lot of evidence why P's could be equal to NP, but that is a whole another topic. But yeah, the reason why people believe P is not equal to NP is that there's this list of very seemingly simple problems. Like 3 color is not even hard to describe. It's just take a graph and use 3 colors to color the vertices. Yet we don't know how to solve this efficiently. Even the Hamiltonian path problem. So yeah, so this is the reason why most people believe P is not equal to NP, because we've not been able to come up with any solution to any one of these problems. But this also means that the way to tackle P equal to NP would probably is, so there's a lot of ways to attack P equal to NP, because you have these huge list of problems and you can attack any one of them. Questions?
Yeah, where can we read more about these things?
I'll uh, um, so I'll put up something on Discord, and I'll put up 3 resources on where you can read more about P versus NP. Also, yeah, so this is a part of a big topic called complexity theory. And these are not the only classes. There's a huge list of classes. So we only talked about something called P is a class of problems, and then we enclosed it in NP. Of course, we don't know if it's a strict subset. So we don't know if this circle of NP is the same as the circle of NP. And then we talked about a small class of problems, although thousands in number, which are like the hardest problems in NP, which are called NP complete problems. And then there are these other problems here in NP called NP intermediate problems. So they're at NP. So assuming P is not equal to NP, these are problems that are not in NP, but are also that are in NP, not in P, but not complete. So there is a problem called graph isomorphism. So you can read about this online, but there's a problem called graph isomorphism, which we believe is NP intermediate. And then we have, of course, this is not anywhere close to done, because there are problems for which even checking if a solution is valid or not is not easy. For example, think of the game of chess. So I have a position in front of me, and someone tells me, look, this is the best move. How do you verify if it's the best move? It's not even obvious how to verify if this move is the best possible. Right? So there are problems which are even beyond NP, for which even checking if it is correct or not we don't know. So there's a huge list of problems outside called NP hard problems, and then of course
Like the chess one which you told, it's manually not possible, but theoretically we can do in infinite time, right?
well, there is a generalized version of chess on n square on an n cross n board, and we actually know that the generalized chess problem. So there is some notion of generalizing chess, just how we generalize sudoku, we can generalize chess. And this generalized chess is in a class what is called P space. So this P space comes outside NP. So it contains NP. P space. In fact, we believe it is. In fact, we know it is P space complete. So yeah. So we don't believe that chess is in NP.
What
believe
is
that
P
it's.
space?
So it's the class of problems that take polynomial space to solve. So I don't want to get into what space is.
So are there
Yeah.
like these questions like, is this space equal to some other space in these bigger spaces?
Yes. So there is something called NP space, and in fact, we know that P space is equal to NP space. Space behaves very differently from time. So P and NP are about times, right? Does it take polynomial time? But P space is about whether it takes polynomial space to solve. and for spaces the behavior is very different. But there are many more questions in complexity theory. It's also called X, which is the class of problems that takes exponential time to solve. So for every problem in NP can be done in exponential time by the brute force method, right? Which is why NP is contained in X. And we actually believe NP is not equal to X. And then there are more classes like NX, etc. NX. And then there's 2X, 2NX. And there are other spaces. And then there are even smaller problems. There are smaller classes than P called L. L is the class of log space algorithms, logarithmic space. So any problem that can be done in a logarithmic amount of space can be done in polynomial time. Yeah, it's like a solar system, I agree. So then there's also a class of problems called co-NP. It's contained in P space. So there is NP, there is something called co-NP, and then P lies somewhere here, and then there's something called RP, which lies here. So this is RP. There's something called co-RP. There's something called DPP. This is a huge list of classes, and there's so much that we do not know. There is so much we don't know. We know that P is not equal to X. There are some results we know. We know P is not X. We know NP is not an X. So X is the class of problems that can be solved in exponential time, and X is the class of problems that can be whose solutions can be verified in exponential time, etc. So much to know, so little time. Yes, and I'm out of time as well. So what I want to say is, in totality, is that complexity theory is a huge domain, which really has a lot of results that are yet to be found, and yeah, hopefully you can take an interest in it, and yeah. So a part 2 of this. Not sure if I want to do a part 2 because, if it gets popular vote maybe, but yeah, it's really interesting. Maybe in part 2 we can talk about what space is.
So, like, is there any sort of introductory textbook or something for these things? Like very.
So the textbooks that I've read from are very rigorous in that sense, but I'll try to find some source which introduces you to P, NP space in a more broad manner and share the resource on Discord. Because since I've studied computer science in college, so someone posted an algorithms.w2f is a good introductory session. So I'll check that out and let you know, and I'll search for other sources. Cool. Questions? Otherwise, we can end the meeting. Rigorous and understand. It's complex because the formal definitions of P and NP, like really formal definitions, I never told you why it's called non-deterministic, right? So what this means, it's because it has to do with something called non-deterministic Turing machines. And so, by the way, I mentioned the name Turing. Alan Turing is like the founder of computer science. I hope you've seen the movie. So does someone know what the movie name is? So it's a movie that features Alan Turing. Yeah, The Imitation Game. Yeah, it's a great movie. The Imitation Game actually is about about him breaking something in cryptography, and the whole idea of cryptography lies it relies on the fact that P is not equal to NP. But what was done was that the system that Alan Turing was trying to break, the people who were using the system, Alan Turing, those people believe that it's very hard to crack, but Alan Turing basically found a polynomial time algorithm to break it. So
What was the system which you're talking about?
it's called something called Enigma. It's complicated, so I don't want to get into that. But the idea is that it's the Enigma machine. There's something, and the people who were so people who thought it was an NP and it's probably NP complete. They kind of guessed that it's NP complete, but it turned out that it wasn't, and Alan Turing was able to put it in P and break it very efficiently, and then was able to take it.
The Turing's machine helped prove that, or like there was some other research also?
No, Turing machine is not an actual machine, by the way. It's a theoretical construct. But he just found an algorithm to break the crypto system. Yeah, well, basically what I'm saying is that the people who believe that so he found an efficient algorithm to do something, and then that helped him decode a lot of things that otherwise could not have been decoded. Usually the idea of cryptography is that one person two people have some sort of a key, and the people lock a message inside the key. So this is a message, and then you lock it inside a key, and then so the problem is that if you simply communicate the message, then someone can intercept the signal. So you communicate the message with this lock K, so that even if someone reads this, they can't really understand what is written. So it looks really illegible to them. So usually in order to break this, you need to know what this key is in order to open and read the message. This is just an analogy, but it turned out that this would be probably some function f of k comma m, right? So then that means without the knowledge of k, it's hard to get m, even if you know f of k comma m, because you can intercept and always get this, but recovering m without knowing k is not obvious. But for the particular f that was used, Alan Turing was able to recover m from f k comma m without knowing k, without knowing the actual k. So usually it involves looking at certain patterns. So for example, let me just state it quickly. So suppose this is a message, and then your idea is to just permute the letters. For example, E becomes Q, and all B's become R, and then all A's become C. So this is not a very good scheme, because in normal English, E appears very frequently. So then in the encrypted, in the ciphertext, in this encrypted message, you can look into which letter appears more frequently, and then these more frequent letters usually correspond to the letters that occur most frequently in messages, and such systems help a lot in decoding ciphertext. So this is called a ciphertext. So yeah, devising this F is very important, and you have to be very careful as to how you can devise F. I hope that made some sense. So cryptography relies basically on P not equal to NP. Okay, I've gone over time. Just any final questions? All right, so then I'll try to put these sources that we discussed, and I'll just try to look up. Yeah.
Like you told many things like P, NP, co-NP, that other different places. So is it like if we prove something, some relation to them, it also corresponds something in P versus NP problem?
Not necessarily, not necessarily. There can be results that you prove that do not necessarily mean P equal to NP. For example, we highly believe that P is not equal to L, but proving that does not do anything about P equal to NP. Or, but there are some other results that may be true. For example, uh, it is true that P is NP imply. I mean, there is something called P slash poly. It's yeah, there are these complicated results, but yeah, I mean there's a lot of there is a lot of relation between the results themselves, but not everything directly implies that P is equal to NP. Some things do, some things don't. For example, X P equal to NX implies P equal to NP, but the converse is not true. P equal to NP doesn't imply X P equal to NX. Or yeah, for example, NP equal to X implies P not equal to NP. That is direct because we know P is not equal to X. So if I can prove NP is equal to X, then obviously P is not equal to NP either. Yeah, so we have some such results, but again, not much that is known.
I meant like if you prove P equal to L, say, then does it like somehow give some progress, you can say, which is like a vague term to say.
Usually, um, okay, so for the particular problems of P versus L, maybe not. But yes, it is true that if you try to prove some two classes equal, then the methods of proof used there translate to the methods of proof used in P versus NP. So there's a whole area about different methods of proof. So methods of proving. So we know a lot of results here. We know that there are certain methods that cannot prove P equal to NP. So we know such results, which is like very weird because that is we know that if our proof is of a certain kind, then that proof cannot prove P equal to NP. So it's almost like a meta complexity theory thing. There's a whole area called proof complexity. Yeah, but yeah, so there can be relations with the ideas. Okay, so I'll stop now because I've gone a lot over time. So I will stop asking if there are more questions. You can ask me offline. All right. Thank you.